Okay, we're going to continue on in the guided notes handout for Module 4, which also corresponds to a Chapter 4, which refers to the PDF that we have in this particular module. So on page 7 in our guided notes, you'll notice that the next thing to work on here is going to be problem 4.4, which is on page 70 in that PDF in Module 4. So I've got page 70 up here. And the problem that we're going to be looking at is going to be problem 4.4. So determine the moment of the forces about point A, B, and C for the cantilever beam shown. Okay, so we are first going to draw a good free body diagram and then at our convention, and then we're going to find what the moments are about each one of those points. So I'm going to add my convention right away. Again, that's per problem. We're adding the counterclockwise rotation because now as we look at summing moments, a moment is a rotation about a point, and a counterclockwise rotation is going to be considered positive. Okay, so let's add our free body diagram. So we're simply going to draw a line, okay, that's going to represent that beam. Okay, so here's the beam, and my line is simply going to start at A and go to C. Okay. So this is going to be point A. This is going to be point C. Actually, I'm going to put my C below, so I'm going to need a force there. And then B is right in the middle. Okay. Now, there aren't any forces at A, but there is a force going straight up at B, and it is 1,000 pounds. And the distance between A and B is 10 feet. The distance between B and C is also 10 feet. And then we have a force that's going at an angle, and it is 500 pounds. Okay, 500 pounds. Now, based on some experience that you've had in statics here, you can imagine that 500 pounds is at an angle. So we're going to have to figure out the components, but we do need to know what the angle is. And in this problem, they are giving us the slope of the line, okay? The rise and the run, okay? So we want to find out what is this angle right here, okay? So we are simply going to find out what alpha is. And we are then going to draw the x and y components. I'll call it alpha or theta. So I know I'm going to relook at my problem. I know if I want to find this angle right here, I have the side opposite and the side adjacent. So I can use the tangent function. So this is going to be tangent alpha is equal to 3 divided by 4. Okay, and there's no units there. It's just giving us, you know, this is the rise over the run. So alpha in this case, then it's like 53 point something. What do you guys get for, I'll put the chat box out, or you can say it verbally. What do you guys get for an angle?
I got 36.8 degrees.
Yep, 36.8. Anybody else?
I got that as well.
Okay, all right. So 36 point, well, it's 86. So I'm going to put 36.869. I'm going to put 36.87 degrees because it's actually probably would round up a little bit. So that's the angle that this is at. And then what we want to do is we want to draw in our x, okay, and our y component. So this is going to be cy and this is going to be cx, just because the force is at c. Okay. And now we want to calculate the components. Okay. So step number 2 is going to be the components of force C. So go ahead and find the magnitude of cy and cx, and I'll do it here. Make sure you have your units in all phases of the problem. So I should be seeing pounds with the 500 here. Did you get 300 and 400?
Yes.
Awesome.
Very good.
Now, here's what I'm talking about. I want to see how you get your CX and your CY. Just don't put CX is equal to 400 or CX is equal to 300. All right. I want to make sure that I can see that you know how to do that. Okay. So any questions so far? All right. So we've got our diagram. We have everything on the X or Y axis. So now we're ready to determine the moments about each one of those points, A, B, and C. So step number 3 then, it's gonna turn the page. Yeah, I don't have much room to do this. I gotta sum my moments around A, all right? So I'm gonna sum my moments around A equal to, right? Now this isn't gonna be equal to 0. We're just gonna now write the moment equation on the right-hand side. So when we do a moment is going to be the tendency of a force to cause a rotation about a point or an axis. So we're going to go about a point here. So we're going to put our finger on A. And just going left to right, I'm going to push in the direction of my first force that's offset. And you're going to notice that my paper would rotate. So that means that there is a rotation. So there is a moment. So when I write a moment is going to be the product of force times distance, and it's perpendicular distance. So in parentheses, we're always going to show our moments in parentheses. If I don't see parentheses, you get points off, okay? Because we want to show in parentheses what the product is, force times distance. That's going to be inside the parentheses. And then we're going to put a sign out front here, okay? So our force is 1,000 pounds. That's the magnitude of force B. Its distance, we're going to multiply the distance. The distance is how far away from A is it? And we say the perpendicular distance. So this has to make a 90-degree angle to the length or the radius. And indeed it does based on the orientation. So this is going to be 10 feet. Units in all phases of the problem. So I have parentheses around my force times my distance. Okay. Now out front, I've got to put a sign. The sign of the rotation is going to come from our convention. So I'm going to put my finger on A. I'm going to pull in the direction of that force. This is going to go counterclockwise. So what is the sign that I'm going to put out front here? Positive or negative? Positive. Thank you, Sarah. Brooke, sorry. Your name is Sarah on here. All right. So positive out front. Then I'm going to continue on. I'm going to look. Oh, there's more forces over here. Let's see if those cause rotation. Now, the reason we broke this into X and Y components is so that we're on the X and Y axis, because with a horizontal line like this, do you see how we get a perpendicular distance then to the Y component of this? Otherwise, we would have to do that business where we would find the perpendicular distance, which is just more math. Okay, so components kind of make that a little easier. So we're going to use first the Y component of that force. So we're going to keep our finger on A and we're going to rotate in the direction of that force. Indeed, it causes a rotation. So we're going to include it as a moment. So we are going to get CY. We don't know what CY is. What am I thinking? This is 300 times perpendicular distance. That's going to be 20 feet total from A. Okay. The next force would be the X component. So if I put my finger on A and I pull in the direction of X, that's CX, does it cause a rotation? No. I'm summing moments, so it won't be included. All right, if I pull this back along its line of action, it's going to go right through that point. It would be a distance of 0, so we don't do anything with it. So our moment about A is just this, okay? So if we sum our moment around A, I thought I needed more room. That's why I went down a little bit. So I just kind of put a little arrow there. So what, oh, forgot. My rotation is also counterclockwise, so we're going to be adding that together. So this is a counterclockwise rotation, and this is a counterclockwise rotation. So the positive out front is for the direction of the rotation that's created about that point. So go ahead and multiply those out and come up with a moment about A. What do you get? Everybody should be working on it. 16,000 pound inches Tim has. Awesome. Yes, that's what I get too. So 16,000, and you have the units exactly right. Pounds times inches. Oh, wait, feet. There we go. Yes. Pound feet. Thank you. Thank you, Tyler. Nope, no problem. I glanced at it and I was going with it because those were appropriate units, but when I was writing it, I noticed it. Yes. So that's one of our answers. So 16,000 pound feet is the moment generated about, yes, it's Friday, about point A. All right, now we're going to do the same thing for points B and C. Now I'm running a little bit out of room, so I'm going to grab an extra piece of paper because on the next page there's stuff. So so I am going to start here. The next one we're going to do is we're going to sum our moments around B equal to. All right. And I'm going to put it directly in back because I think I can fit it. So this time what that means is when I say sum the moments around B, that means I'm putting my finger on B. Okay. Now, if we look here, there's no force at A, so there's nothing to include on that side. But there is a force at B. If I pull in the direction of that force, notice it does not cause a rotation. So when a force is going through a point, it is not going to be included in our moments, okay? So then we just move to the next point, and over here, that's going to be our C. And our CY is the one that's offset. So if we rotate there, it causes a rotation. So our CY, we know that to be 300. And that's pounds. And from B, the perpendicular distance is 10 feet. Okay. And now again, the direction of rotation will be the sign out front. So CY. And that's going to be a positive counterclockwise direction. Now, as we look at CX, does not cause rotation. So it's not going to be included. So the only force offset causing rotation is going to be the 300 times the 10 feet. So sum the moments around B. It's going to be equal to, what's our number?
$3,000 foot-pounds.
Yep, 3,000 foot-pounds. That sounds correct. So 3,000 pound-feet. Remember, in moments, we always want to do pound-feet. Foot-pounds is what? What did we say foot-pounds was for?
Torque?
For torque, right. We are not determining torque here. We are determining moment. So we always want to put the force units first and then the distance, just like we write them. Okay. Good. So box around that. And then the last one is going to be summing your moments around C. Go ahead and do it. Okay. I'm going to let you do this one, and then I'm gonna hesitate for a little bit and then I'll write it in, okay? Okay, for this one, we're going to put our finger on C this time, right? And by doing so, we eliminate CY, because it's going to push, and CX. They're not going to be included, but the offset force at B is going to rotate. So I'm going to put my parentheses, finger on C, rotate in that direction. It's going to be 1,000 is going to be my force times perpendicular distance, 10 feet. And then the sign out front is going to be negative because this is a clockwise direction. Okay. So we multiply those out, we're going to get a negative 10,000 pound-feet. So a couple things when we write our moments out, they go in parentheses. Do not put them on. And the reason for that is because the sign out front is based on the direction of the rotation that's created by that moment. And the moment is a product of force times distance. So you have to put the parentheses around. Make sure that you put your units in all phases of the problem. If they're not there, you will lose points. Okay? And then when you put your final units in, this is multiplying force times distance. So pound feet, pound inches. Okay? So any questions on this one? Okay. So then that means we get to turn the page. Okay. So on page 8, this is just a little quick review of what we've done so far. So see how many things you can fill out on this page. Okay, go ahead and fill in the blanks. And for those, if you don't have this printed out, you're going to have to duplicate this when you hand in your practice problems. So not only the examples, but also these items where we have things filled in. Okay, why don't we start looking at the items that are on here, okay? I'm gonna zoom in. So first of all, draw the new convention. And really the new convention is built from the original convention. So our new convention, which includes the rotation, is gonna look like this, right? It's the new convention. It's at the top of every one of our problems, every one. The next part here, all forces pointing up and to the right are considered positive. Okay. And all moments causing a counterclockwise rotation are also positive. And that's what we get all from the convention that we see above. Moments are the tendency of a force to cause rotation about an axis or point. Okay, and we see examples of both regularly. The magnitude of a moment is calculated by multiplying the force times the perpendicular distance back to that point. write the moment equation in variable form. So sum, capital M, not small m, capital M. And then I'm going to say sub-zero, kind of like an origin, but this would be the call out of your point, is equal to force times distance. And I'm going to put a positive or negative out front. My equal sign back a little bit. Positive or negative. And that positive or negative is going to be based on the convention, right? Which is the direction of rotation. This is going to be our force. This is going to be the perpendicular distance. The symbol sigma, capital sigma, is sum of, right? Capital M is moments. And then this is going to be the point or axis. Put it in there. Okay. All right, so let's write out our units for the following. Moment, remember, we don't want to use inch pounds, foot pounds, because that's torque. This is moment. So the units for moments, and I always put these in brackets, are going to be pounds times inches. Pounds times feet. Okay, force times distance. Kips is another one. So there's multiples. Additionally, if we're in metric units, it's going to be newtons times meters or newtons times centimeters. Okay, so just a couple versions of the units. For force, the units are going to be pounds, pips, newtons, kilonewtons, and again, multiple versions of when we have, different versions of. And then distance. Distance can be inches, feet, meters, centimeters. Okay, any distances that kind of go along with the scale of the problem. Any questions on that? It's always important to know your units. Throughout the program, you're going to find that the emphasis on using units, knowing what you should be getting, verifying that you indeed do get that throughout the problem, then you have confidence, if you would, in your final answers if you get the correct units. Okay. The next statement here, it says the sign out in front of the individual moment identifies the blank of rotation, identifies the direction, right, of rotation. And we compare that back to our convention. So the direction of rotation, not the direction of the force, okay? We don't look to the force as an up, down, left, right. That's some of the forces. When we sum moments, we are looking at, is it clockwise or counterclockwise? So counterclockwise equals positive, clockwise equals negative. Okay. All right. Any questions on page 8? Oh, let's do another problem. We're going to do problem 4-5 on page 70. Okay. So going back underneath here, this is the PDF. 4-5. This is a good problem. Okay. Says here, determine the moment of the forces shown about D, E, F, and G. So we've got a grid here. Okay, and we've got some forces. 2 of them are at angles. 1 is horizontal. And then we've got points D, E, F, and G. And they want us to find the moments about each one of those points. Okay. So first things first, you got to draw a good free body diagram and add your convention. Okay. So we're going to duplicate what we see here. And you're going to notice that starting on page 9, the area in this area right here. So above, right in here, this is how we're gonna use this space to draw the diagram and then add any additional information that we need. Then we're gonna be breaking the forces into components down here, okay? And then turning the page, then we're gonna sum the moments on the backside. So we've got plenty of room to draw a nice large diagram, okay? So that's what I'm gonna do over here, and I'm gonna add my convention upper right-hand corner. Okay, so my convention is on here already. So I'm going to add all the information for this problem. And you want to go ahead and do that very same thing as well. So let me see here. 4, so there's 4. I'm gonna draw my components right away so that I have them on here, and then we can calculate their magnitudes below. I'm gonna call this. Call it F1. X, Y. So don't be skimpy on your diagram, okay? Because you've got to add some units in here. I did draw mine kind of to scale. I kind of went, I think, 2 centimeters for each one of my divisions, but doesn't have to be perfect, but needs to resemble and be proportional to what we have here. Okay. Now that we have our diagram in place, then the next thing we're going to do is we're going to determine the magnitude of each one of the components. And that's the space that we have down here. So I am going to do my F1X and F1Y first. So as we look at the angle that was given, it was 50 degrees and it's here. So that means that for my X component, it's the side opposite. Okay, so technically 50 is here. Okay, so that means that I would use the sine of 50 degrees. So F1X is going to be sine of 50 times 25 kilonewtons. So F1X F1Y is going to be the cosine of 50 times 25 kilonewtons. Again, showing your work, units in all phases. F2X, it's going to be up here. We're given, we're given the fact that this comes back here. Since the legs are both 1 meter and it bisects or is in line with, that means that this is a 45-degree angle. Okay, because each one of these lengths is the same amount, 1 meter. So that's 45 degrees. So then we can calculate the X and the Y components here. So cosine 45 times 20 kilonewtons. It's going to be 14.14 kilonewtons. And then F2Y is going to be sine of 45, which is the same as the cosine of 45. Again, writing everything out. And that's going to be 14.14 kilonewtons as well. All right, any questions on the components right now? Everybody get the same values as I did? Everybody get the same that I have here or not?
I did, yeah.
Okay, thanks, Josh. Anybody else?
Same here.
Thank you, thank you. Okay, thanks, Brooke. All right.
Yep, got it.
Awesome. Thanks, Danny, or I'm not sure who. That was Danny. All right, awesome. So now that we have these, now we're ready to do the sum of the moments around each one of those points. So we're going to do 4 moment equations. The first one is going to be about D. Okay, so there's room on the next page to write these. Okay, what I'm going to do just for ease of showing it on the camera here, I'm going to scooch this back a little bit. Okay, I'm just going to start a new piece of paper underneath and then write them underneath here. So the first one we're going to do is we're going to sum our moments about D. So we're going to use our summation symbol, capital M sub D is going to be equal to, and then we're going to write out the equation left to right. Now, which force you start on doesn't really matter. So I'm just going to work from D and go around. Okay. So I'm going to put my finger on D, and the first force that I come up to is going to be my F1X. If I rotate in that direction, it's going to cause a rotation. So F1X is going to be included. F1X down here is the magnitude is 19.15. So we're going to put that in here. 19.15 kilonewtons. Okay. Times its perpendicular distance from D. We're going to go straight up, and this is going to make a 90-degree angle. So 2 meters. Okay. Direction, out front, we have to put a sign. So if I pull in the direction of that force, it is going to be counterclockwise, which means we're going to be a positive rotation out front. Okay. I want to show you that this force, F1x, is pointing to the left. A negatively directed force is causing a positively directed moment. This is rotation. This has nothing to do with this being left or right. It has to do with where it is in relationship to the point that we're summing around. Okay. Put my finger on D. I'm going to pull in the direction of F1y. Does not cause a rotation, so we don't include it. But you'll notice up here, F2y does. So F2y is going to be included. So I'm going to leave some space here, start my parentheses. F2y is 14.14 kilonewtons. Okay. Perpendicular distance. Okay, perpendicular distance. D is down here and F2y is up here. Principle of transmissibility. If I pull that all the way back along its line of action, I can reposition it, if you would, right here. It'll have the same net effect on the body. Perpendicular distance is 2 meters. See that? So this is going to be times 2 meters. Now, direction of rotation. If I pull in the direction, I kind of try to go like this. There we go. It is going to rotate counterclockwise. So that means that's a positive out front. Counterclockwise. Counterclockwise. Again, that's the direction of the rotation, not the force. That's why you have to put the parentheses, because we're giving the sign to the moment, which is force times distance, not just to the force. It's the product of force times distance. All right, our next one, finger on D, pull in the direction of the F2x causes rotation. F2x magnitude 14.14. So I'm going to go 14.14 kilonewtons times, okay? Perpendicular distance. So D is here, F2x is here. We're going to pull it back along its line of action, and it would be, if you would, imagine it right here, principle of transmissibility. So now if I look, that would cause the rotation. I'm 1, 2, 3, 4 meters away. So its distance is going to be 4 meters. Okay. Sign out front. If we put our finger on D, pull in the direction, it is going to cause a clockwise rotation. That is going to be a negative. Negative. So this is clockwise. Running out of room. That's okay. So then I'm going to add one more moment, because that's going to be my 50 down here. Okay. So put my finger on D. I'm going to notice that, yep, it causes a rotation. It's offset. So I'm going to have 50 kilonewtons times perpendicular distance. We're going to pull it back along its line of action as if it were here. And its perpendicular distance is going to be 1 meter. Now, we have to put our sign out front, direction of rotation. So if I look at D and I pull in that direction, that is going to be a clockwise rotation. And according to my convention, that is going to be negative. Okay, so I'm going to go like this, clockwise. So my whole moment is, I have 1, 2, 3, 4 moments total. So don't forget to add that one in there. So the sum of my moments around D, we're going to multiply, add and subtract, and we're going to get a value. So go ahead and figure out what the total moment around D is going to be. Thank you, Tim. You got the same answer as I did. Excellent. And I know that to be, yep, that's what I got. Thank you, Brooke.
That's what I
Awesome.
got too.
Fantastic. So yes, that's the answer. Okay. Let's do our next one. 3 more moments to do. All right, our next one, we're going to go around E. Okay. So I'm going to make a little line here. Sum by moments around point E equal to, I'm going to maybe write a little smaller, see if I can get them all on this time. Point E, and I'm going to work clockwise around. So the first one I have is going to be F2Y, right? F2Y, kind of bring this down, is going to rotate in a counterclockwise direction. So the moment is going to be positive. And then F2Y times its perpendicular distance, 1, 2. So I'm going to have a positive out front. F2Y was 14.14. Okay. Kilonewtons times perpendicular distance, 2 meters. F2x pushes through. It doesn't cause a rotation. No moment for that one. Then we're going to move down to 50. Finger on E. 50 does rotate. It rotates in a counterclockwise direction. If we pull 50 back along its line of action, from here, it's going to be 1, 2, 3 meters. It's going to be the distance. Okay. So, parentheses, 50 kilonewtons times 3 meters. And the sign out front, E, counterclockwise, so positive. Okay. Put our finger on E, pull in the direction of F1Y. It's going to push through. It is not going to cause rotation, so we don't include it. But F1X will cause rotation. So F1X magnitude is 19.15. Perpendicular distance from E is 1, 2, right? And then the direction of rotation is going to be clockwise. So that's going to be a negative out front. So negative out front. F1X 19.15. And perpendicular distance was 1, 2. Okay. And those are all the forces, we made it all the way around, that are causing moments on point E. So if we sum our moments about point E, so you should get 139.98 kilonewton meters. Remember, not kilonewtons per meter, because we're not taking force divided by distance. We're taking force times distance. So our units are going to multiply. Okay. Just want to make sure I get a confirmation. I'm working the problem with you guys, and I don't have the final answer in front of me, but that number sounds familiar. I got 139.98. Thank you, Nicholas. I appreciate it. Awesome. Me too, Brooke. Awesome. Okay, then we'll call it confirmed. All right. So we got to do our next moment. Our next moment is going to be about point F up in that corner. Why don't you go ahead and see what you can do for this one? And then we'll go through it together. I'll kind of hold back a little bit. So sum your moments around F, see what you get for a total moment around F. Had something different both times.
So there are people commenting in the chat.
Oh, yeah, I see that. Okay. Hold on. Is F1 3 meters away or 2? Let me see. F1. Oh, it's 3. I think I did. Did I do 2? That's okay. That's why we check it. 16. Oh, no. F1Y. And then F1X is 2. Yeah. So F1. Well, remember there's an F1Y and an F1X. So you have to do both of them separately. I'll go over this in just a second. But thank you, Tim, for adding. I'm just double checking mine right now. Number twice. Tim, you got the same. Awesome. Looks like Connor got the same, and we'll talk about our numbers in just a bit. Okay. Got the same. Excellent. Okay, you guys. Good, good, good. So starting with F, and I started working around again clockwise. So I started with my 50. So F, and it's going to cause rotation, and 1, 2, 3 perpendicular distance. So positive counterclockwise rotation, 50 kilonewtons times 3. Then I worked over here. I started with my F1X first. Okay, F1X. We go on F here. It is going to cause, sometimes I rotate, sometimes I don't. There we go. It's going to cause a rotation. F1x is 19.15 kilonewtons. And if we move this back along its line of action, it's going to be 2 meters away. So 19.15 kilonewtons times 2 meters. And when we pull in the direction, it would be a clockwise rotation, so negative out front. Okay. The next one is going to be F1y. F1y also causes rotation. F1y's magnitude is 16.07. So 16.07. And then if we move this straight up, its perpendicular distance is going to be 1, 2, 3. So both components have a distance associated with them. So 3 meters here. Negative out front because it's going to be another clockwise rotation. And then the last one that we have is right up here by F. This is F2y. It is going to cause a rotation. It is only 1 meter away. Okay. And F2y, 14.14 times 1. It's right here because I ran out of room. And then a negative out front because it's going clockwise. Right. F2x passes right through that point, so it is not included. All right. So if you add and subtract here, you should get the moments around F are going to be 49.35 kilonewton meters. And it looks like we got a confirmation of a couple people. Right. So we've got one more point to sum around. So go ahead and sum your moments around G, and I'll kind of hold back again, and then we can compare. Okay. So G down here. See what you get. Okay, why don't we start looking at it? I didn't write mine out yet. I thought I would develop it as we go here. This will be our last one for this problem. So G is the point that we're summing around. I'm going to, again, work clockwise around. So I'm going to go up to F1x. So as I look at F1x here, it is going to cause rotation about G. So I have my sum my moments about G. I actually fold this one more time. That way we're not looking at two sets of numbers. Okay. So sum my moments around G. So F1x is 19.15 magnitude times from G perpendicular distance back, okay, 2 meters would be the perpendicular distance. And then it is going to rotate in a counterclockwise direction, so positive out front. F1y, that will cause a rotation as well. F1y, 16.07 kilonewtons times perpendicular distance. I'm going to kind of pull this back along its line of action, and it would be 1, 2, 3 meters away from G. And then as I pull in that direction, that is going to be a clockwise rotation, so negative out front. Okay. Finger on G, F F2Y. F2Y, yep, that'll cause a rotation. It's offset. If I pull it back along its line of action, its perpendicular distance is going to be 1. And F2Y is 14.14 kilonewtons times 1 meter is the distance. And then direction of rotation is going to be clockwise. So we're going to put a minus out front. Right. And I have to go to my next line here. So finger on G, I've got my F2X, going to cause rotation. And its perpendicular distance is going to be 1, 2, 3, 4 meters away. So F2X is 14.14. And it's going to be 4 meters. And then direction of rotation, finger on G, it's going to rotate clockwise. So negative out front. And then the last force that we have is going to be the 50 kilonewtons. So finger on G, pull in the direction of 50. It rotates, so 50 kilonewtons times, we can see that it's 1 meter away. And then it is going to rotate clockwise as well, so negative out front. Okay, so now we're ready to add, subtract. Me a little bit here. Times. Oops. I think that sounds right. I only did it once. Did anybody else get the same number?
I did, yeah.
You did. Okay.
Yeah, I
Excellent.
did too.
I didn't want to go through it a second time. Good. Good, good, good. Okay. So moments. I'll leave that up here for a little bit. This is going to be, again, some of the forces in the X, some of the forces in the Y, looking up, down, left, right, but now these rotations, the tendency of a force to cause a rotation when it's offset from the pointer axis that we're looking at. We're going to continue to use these all the way through too. So these are the foundations of all of the design courses that you're going to be taking from here on out. So a very important subject. We're going to get a lot of practice and take our time with this. All right. So as we look at our handout here, this is the last example that I wanted to be sure that we got through tonight, the last problem. So this is where we'll stop. I'm gonna stop the recording here, and the next time that we're together, we will continue on in our handout. So I'm gonna stop the recording.